team, I'm Maddie, welcome to ScienceSideUp, and today we're going to talk about some real-life science. Bonus video this week, be sure to like and subscribe, team. So yesterday I gave my annual seminar at school, which is where I have to talk about my research for about half an hour, and I recorded that for you guys. I hope you enjoy.
Good afternoon, I'm Maddie. Today we're going to talk about atmospheric conditions that precede very rapid sea ice loss events. So this is a lot of my master's work with some of the upgrades I've managed to get done over the summer, especially following some nice feedback I got at AMS Polar back in May. So let's just jump into things, shall we? So first, for those that don't look at the Arctic every day, we're going to talk a little bit about TPVs, Arctic cyclones, and sea ice, and just the Arctic environment. And then I'll go into what a very rapid sea ice loss event is. Then we're going to go into kind of just a case study example of one, and then we're going to, in a composite sense, look at what the atmospheric conditions that precede these very rapid ice loss events are, and then talk a little bit about conclusions and future work and why I'm staying for a PhD and all that jazz. So let's talk about the Arctic. So brief tour of the Arctic. If we're talking about Arctic sea ice, here are some nice pictures that I snagged from NSIDC, so National Snow and Ice Data Center, to give you an idea of what sea ice extent looks like in the winter on the left versus the summer. And when we're talking about sea ice, first we're going to talk about why we care about the Arctic. Why should we care about the Arctic? Apart from sad polar bears, we definitely care about the changing environment that's the Arctic. As the Earth continues to warm, the Arctic warms at twice the rate as the rest of the planet. So we're seeing a lot of in that region. You see a lot of changes happening really rapidly. There are the population of people that live in the Arctic as it warms is continuing to increase. So you're seeing population growth in that region. And so we definitely care about the weather for the humans that live there and the ice conditions. Wrong direction. Cool. And last but certainly not least, as we're continuously losing sea ice and moving towards a sea ice free September, where shipping lanes are opening up that have never been accessible before, as well as natural resources are becoming available that have never previously been available. And so a lot of what I'm looking at relates to ensuring that ships and things can traverse the Arctic sea lanes safely. We definitely care about the dynamics of that, changing environment. Okay. So back to our brief tour of the Arctic. I want you to think about the question of how does one lose sea ice? Well, the easiest way is for the sun to come out in the summer. And we definitely see that if you look at, this is a Fourier transform of sea ice extent, and we're looking at the specifically sea ice extent changes. And so we see an incredibly strong annual cycle that goes off the chart. And so the sun coming out in the summer is certainly an incredibly important signal. But I'm more interested in those peaks that are showing significance at shorter timescales. And specifically, I'm interested in the sea ice loss on synoptic timescales. So getting towards some Arctic cyclone stuff and why we think that might be associated with the shorter timescale ice loss events. This is a figure from Zhang 2004 that looks at climatology of Arctic cyclones. So I want to point out that in the winter, we're seeing you have these hotspots of cyclone activity right along the sea ice edge. So that might be something that's important. In the summer, cyclone activity is much more spread out. It's not nearly, you don't get as many hotspots. This one over Greenland, that hotspot over Greenland is very potentially Greenland's topography is kind of a known problem in the Arctic. It's very high, and so you often get hotspots and data right on top of Greenland that may or may not be real. So just don't trust Greenland. That's a good takeaway for Arctic research. But anyway, so the cyclone activity in the summer is much more spread out across the whole Arctic, so we don't see those same like hotspots of cyclone activity associated with sea ice edge, but we certainly do see cyclone activity around the sea ice edge. And so then the question comes, well, how could a surface cyclone, affect sea ice loss? And the data that we have from this has to do with observations of like individual cyclones interacting with sea ice. So these are like from observations. And the two ones I want to talk about right now are the acceleration of sea ice flow breakup and driving ocean surface waves into the marginal ice zone. So sea ice flow is like the thing the polar bear is standing on. There are these like large chunks of ice that are in what's called the marginal ice zone, which is a transition region between the open ocean and the solid ice pack in the central Arctic. And so if you have really strong winds from a cyclone, and those are maybe inducing ocean waves, then you can accelerate the sea ice flow breakup. So we could physically break up a big piece of ice and make it a smaller piece of ice and make that easier to melt. And then you can definitely drive ocean surface waves pretty deep into the marginal ice zone that's been observed. So you can get that effect like pretty deep, the effect of breaking up the sea ice, mechanically breaking it up. You can definitely see that. So briefly on tropopause polar vortices, for today's context, the important thing about TPVs is going to be that, especially in the Arctic, they're an important mechanism for both cyclogenesis and then strengthening cyclones in the Arctic. And so we'll see TPVs come into play when we start looking at our individual events. And then the last point on here about mixing, surface cyclones can mix warm ocean water up from beneath the freshwater cap. So for those maybe not super familiar with the Arctic Ocean, in the Arctic, the density of the seawater is predominantly a function of salinity, not temperature. So what you end up with is warm, salty Atlantic water beneath relatively cold but less saline Pacific water. And so if you have strong enough surface winds, you can induce that vertical mixing and bring up warmer ocean water from below that fresh water, which can again enhance melt. So it's kind of counterintuitive. Okay, so that is our brief tour of the Arctic, and now let's talk about what a very rapid sea ice loss event is. Very generally speaking, it is when you lose a lot of sea ice in a short period of time. Probably the most well known is the sea ice loss that's associated with the Great Arctic Cyclone of 2012. So what I'm showing here is just satellite images from like NASA Worldview with sea ice concentration overlaid from on the left, day 1 of the Great Arctic Cyclone, and on the right, the last day of the Great Arctic Cyclone. So the September 2012 remains the record minimum sea ice extent that we've ever measured. And this one event is associated with like 4.4% of the total sea ice loss for that summer. And you can see that really dramatic change in those satellite images. If we actually jump into the sea ice concentration data and take like the difference, that yellowish looking blob is this like the largest connected region of loss in the 5-day change in sea ice concentration. And so we see this very large loss of sea ice over a short period of time. And so Great Arctic Cyclone is a very well-known event, but we would like to have a way to like systematically identify these types of events. So to do that, we're gonna go look in sea ice extent data. So you take the daily sea ice extent, that's the data set you have back from 1979 to present, and then you can take the daily changes, smooth that with like a 3-day running mean, and then, so now you have this data set of changes in sea ice. And then we're going to filter that in one of two ways. One thing I wanted to point out is if you see that little sharp drop in the orange curve there, that's something that happened in February. So I'm getting at you can have these large sea ice loss events even in the winter. Okay, so we have two different methods that you can use to filter your daily changes in sea ice. One would be to just remove the climatological mean state, represented by that like dark gray curve. And that would be a good idea if what you were interested in is like how does climate change affect the frequency of VRALs or the strength of a VRAL or the size of one. And the other method, which is the one that from this point forward in this presentation, if I'm presenting data, it's been filtered in this way. We're going to apply a Butterworth filter, use it as a low-pass filter, and exclude anything with a period greater than 18 days. 18 days is selected because if you looked at this zoomed-in figure down here on the bottom right, you see I have a significant peak that's a little greater than 15 days, but nothing significant down in these shorter time scales greater than 20, so 18 is a pretty good choice. So we're going to capture all of those significant peaks and remove the annual cycle and those larger time scale types of things. So in my master's thesis, I did any image you're going to see today. I exists twice because it exists for both filtering methods. And the moral of that story was, for my purposes, we're looking at those atmospheric conditions. There's no qualitative difference between the two filtering methods. So from this point forward, everything is using that Butterworth filter. Okay. So once we've filtered it, you take the bottom 5% of events, and we call those our VRALs. So those are the events that we have identified in time. And that's all well and good, but then we have to find them in space as well. So to find these VRALs in space, you take the 5-day change of sea ice concentration, and then find connected regions of loss. So for example, this is the difference in sea ice concentration between August 7th and August 2nd, 2008, and we identified that a VRAL exists on August 7th. If you find the largest connected region of loss, we will call that the VRAL. And whenever possible, I will use the whole object, but sometimes we'll need a specific point to say this is where the VRAL occurred. And for that, we're going to do a sort of center of mass calculation. So you weight every point within the ice loss object by the absolute value of the change in sea ice, and then do that weighted average, and then that's your location. So this is a place where I'm differing from my master's work. In my master's, I used the point within the loss object that experienced the greatest negative change. And so you can see for this particular object, there's a pretty big difference in the location. And I actually really like this example. We'll go through more of it later. I like it because the shape is so odd. So kind of some of our methodology can work for this odd-shaped thing. It should work for the more globular events like the ice loss associated with the Great Arctic Cyclone. Okay. So here are the VRAL locations, those individual locations plotted for the winter on the left and the summer on the right. The main difference, so this is what it was, these are those locations beforehand when I used the point of greatest loss. So I'll kind of toggle back and forth. And what I see as the main difference is that with the center of mass location, they're actually more grouped together, which I find kind of interesting. So a few things that I'm going to point out. One is we can see pretty clearly that in general, these loss events are occurring at the sea ice edge, which is pretty expected. That's where the ice is going to be the thinnest. And then we're also seeing, especially for the winter, sea ice loss events, those VRALs being concentrated in the centers of cyclone activity. Again, that's harder to identify for the summer. Okay, So that is what a very rapid sea ice loss event is. And so now let's dig into that August 7th from 2008 example. So on the right here is the just a histogram of the magnitude for the sea ice extent change loss. And this August 7th virile is that little green dot, so it's actually really small compared to these sort of other events. So this guy is kind of not super impressive, and I liked that as one of the reasons I chose it, because there's not anything written about this event, and it is kind of oddly shaped. So, you know, if it works, if things work for kind of the least impressive event, then they should hold true maybe for the more impressive ones, hopefully. So what you're seeing here is the red and blue is that sea ice concentration difference. Our yellow blob is the ice loss, is the virile itself, and then the aqua-colored curves, there's 3 of those. Those are Cyclone Tracks from INSEP NCAR reanalysis. And so these are the tracks of Arctic cyclones from INSEP NCAR reanalysis that passed within 1,000 kilometers of the ice loss object no more than 5 days before the virile occurred. And one of the things that I'm working on is, so we have an in-house tracker that we use for TPVs, and I would like to use that tracker for surface cyclones, and then be able to have like TPV tracks and surface cyclone tracks that I can compare and talk about together. So that image that I just brought up is all of the cyclones that our tracker found. Our tracker works differently than the INSEP NCAR. Ours uses a watershed method, and it's better at capturing splits, so you sort of get more events. And I also didn't restrict it to a definition of Arctic cyclones, it's just any cyclone. So I'm getting kind of too many cyclones right now when I use our in-house tracker, but that's part of that like work in progress. Let's take a look, kind of issues with in-house tracker aside. Here is that one main cyclone. The ice loss object is plotted in gray. The color on the background is potential temperature on the dynamic tropopause, taken to be the 2 PVU surface. And then the light gray contours are mean sea level pressure. I've got them contoured every 10, I think. And so I've got a little movie for you guys. So you can see that surface cyclone follow the red track, and it is wrapping a TPV up around it as it goes. Let me play that again. So I would watch this thing kind of develop there. There's a surface cyclone, and there it is wrapping in that TPV. So one thing that I liked, that I found interesting about this particular surface cyclone is that, yes, the shape of this virile is really kind of elongated and a little strange, but there's a cyclone that wraps all the way around it and kind of traces it out. So I thought that was pretty cool when I saw that. So looking at a still image, same fields as before. This is from August 4th. The things I wanted to point out are, one, you can really see the TQV and surface cyclone pair. And then the other is that if you look in the mean sea level pressure, what you see is a pretty strong pressure gradient that's directed towards the virile. So our key takeaways from this example is that the virile has an associated surface cyclone. That cyclone has its little TPV that it's paired with, not little TPV. And then there's a strong pressure gradient that's directed across the virile. And so then the question is, do those 3 things exist for viriles in general? And to look at that, we're going to take a look at some composite means. So these are composite means. They go from the day of the virile back to 5 days before. The fields you're looking at, the red and blue, is standardized anomalies of potential temperature on the dynamic tropopause. And then the gray contours are standardized anomalies of mean sea level pressure. They're contoured every half sigma. And the gray stippling indicates regions of statistical significance at 99% based off of bootstrap resampling. So so these are centered on the virile itself. So I take that center of mass location, I grab a 6,000 kilometer box of data around it, and then I project it into an evenly spaced map space. Do that for all of my events, take the mean, and then this is what we get. What I find most interesting about this figure is that pressure gradient that's happening across the virile itself is strongest 2 days before the virile actually occurs when we're looking in the winter. But if we look in the summer, we still see that nice pressure gradient signal, but it's strongest the day of the virile. So that was the main difference between the seasons that I kind of take away. Some other composites I've got for you are, we're going to recenter the composite. Instead of being on the ice loss location itself, we've moved to the closest local minima in mean sea level pressure, and then recentered, reprojected, taken the mean. So we see a nice clear surface cyclone signal, and we're starting to see the signal of the TPV come out. So there's the winter and summer, and both of those, again, nice strong surface cyclone signal. And then we're going to recenter one more time on the TPV, so the closest local minima in potential temperature on the tropopause to the virile. And the only difference here is that in the previous figures, statistical significance was shown for the mean sea level pressure field. Here it's being shown for potential temperature. And so yeah, you can still see a pretty clearly defined surface cyclone, and then you see the TPV with it in the winter and then the summer. So looking at those, the mean sea level pressure centered composites and the TPV centered composites, one of the things I looked at was, so this is looking at the horizontal distance between the center of the TPV and the center of the surface cyclone. So on the left is the winter, this is from the composite data. On the left is the winter, on the right is the summer. In both, the blue curve is from the mean sea level pressure centered data, orange is TPV centered. So notice that the blue curves are sort of all over the place. And if we think back to the mean sea level pressure centered composites, the TPV is less defined. So I'm not particularly surprised that the data from those composites is a little all over the place. And then the orange curve is from the TPV centered ones. And so what we're seeing here is that, to me, kind of the overall story is that the TPV and the surface cyclone are getting closer together as time goes forward. So this figure actually changed a decent amount when I switched from, this is for the center of mass to virile location, and that's for the point of greatest change. So these figures tell, I think the orange curves tell a little clearer story, and so than the new figures do. I calculated everything the same way. So this is one of the motivations for why I want to get into actual tracks of TPVs and surface cyclones and see how that coupled system evolves prior to the virile occurring. And then this is the strength of the surface cyclone as defined as the minimum mean sea level pressure. And this story didn't really qualitatively change between the center of mass versus the point of greatest change for those different virile locations. So what we're seeing, right, is that in the summer, the surface cyclone continues to strengthen right up until the day of the virile. But in the winter, the surface cyclone is strongest 2 days before the virile occurs, which matches what we saw in the composite data for the strongest pressure gradient in the winter being 2 days before the virile. And so that is something that I find really, really interesting. So what I think is going on there is this difference between winter and summer events. And so I think it's important to kind of think about like what's going on in the winter versus the summer. So in the summer, it's the tendency of the ice to want to melt, right? Because the sun is out. So you're having this like thermodynamic forcing on the ice that's thinning it, that is potentially making it sort of ready for a virile to occur. Because hopefully I've convinced you that viriles tend to be preceded by a surface cyclone, right? But most Arctic cyclones don't result in a virile. So a big open question is sort of what's the difference? Why do some cyclones result in a virile but others don't? And so I think a lot of that is going to be in the ice conditions. And that's looking at some of my PhD work. I want to dig, kind of first steps there are digging into those ice conditions using some modeling tools. But in the winter, the sun is not out, right? It is the tendency of the ice to want to freeze and not melt. And so if we're gonna have one of these major loss events, I think that you need to have you have to do a little work on the ice beforehand. So I think what you have is the cyclone itself, doing some of that, maybe like breaking up some of those flows, right, getting our pieces smaller, and now the ice is vulnerable to one of these major loss events occurring. So that's kind of what I think is going on, and I'm really excited to dig into that with some modeling studies with my PhD as I start that. So that is all I've got for you guys. I'll let you watch sea ice decline over like decades as I take any questions you might have. Hi, Cameron.
The composite analysis is really interesting. And I was curious, do you know how the liquid ice boundary overlaps with that pressure gradient that you see kind of centered on those events?
So I think your question is,
Because it's centered on the ice loss event, right? How is this juxtaposed with the area where you postulate as being most vulnerable to ice loss, right, being along the edges?
Gotcha. So I definitely think that this is in the marginal ice zone, right, which is that region between open ocean and sea ice pack.
Right.
I have looked at, or attempted to look at, sort of how, what the sea ice looks like underneath this. And so I did a lot of stuff with sea ice concentration, and no real discernible signal came out. So I do think that what you've got going on is strong pressure gradient kind of along the edge, though the sea ice edge is not as firm and solid a boundary as we would like it to be. It's more of a fuzzy, kind of fuzzy region. But I think it's those strong winds directed across that marginal ice zone.
Yeah, because if you imagine the ice being more concentrated in the upper left-hand portion of this graphic. Yeah, upper left-hand portion.
Right.
That would make sense, right? Because then you overturn the circulation and bring up the warm waters and eat away at that, that edge, right?
And that's, if we kind of look at this, in this case, we've got these winds kind of, in the specific example, they're sort of directed, not necessarily, you would sort of expect it to be coming from open ocean across. So the winds are directed kind of differently. But yeah, the wind direction relative to sea ice edge is certainly an important component. Does that answer your question?
Yeah, I
We're close enough.
really had a good answer. I was just curious.
I may have just missed this, but how many VRILs were you able to identify that go into these composites, and over what time period was that?
Oh, sorry, I think I forgot to say. Summer, there are between 1979 and 2018, 79 events. In the winter, it's actually like 140.
Okay.
Yeah.
Do you know why people are moving into the Arctic?
Why are population is increasing everywhere?
Oh, okay. Yeah, I guess that makes sense.
Land is cheap.
It is also, land is cheap. There's regions that are more accessible now than they were like 20 years ago.
Yeah, that's true.
I actually read a whole paper on that.
I figured
that was, yeah.
It was interesting.
Yeah.
People literally seriously live there?
Yeah.
Are you kidding?
No.
I thought it was like in half.
No. There's whole, actually, like CAs and indigenous people. There are tribes that like hunt on the CAs, and the CAs is changing too rapidly for their own local maps to keep up with. So more than once, you've had like these people and their sled dogs get like stranded on ice and have to be rescued. Yeah.
Towns up and out of it are exploding because of the Northwest Passage opening up now too.
Yeah.
So now shipping routes are open and explode, like huge population explosions.
Yeah.
Cambridge Bay, for instance.
I know at least for a little while, wasn't Alaska like as a state like giving people like money if they move there to work there permanently? They're trying to increase the local.
Oh, Alaska is a great place to move right now. So yeah. Also, so I think this image cuts off at about, yeah, because Hudson Bay is like, that's like 55. So if you take the Arctic to be anything 60 north, right? There's definitely people that live up in there. Yes.
There's a lot of this analysis is focused on more surface cyclones. I'm curious if there's any of these type of events associated with like strong anticyclonic wave breaking, like in the Kara Sea or things like that, like high, resulting in very anomalously high temperatures and stuff like that.
So I haven't specifically looked at anticyclones. I have some stuff that's not in this presentation. I've used that like NCEP and CAR reanalysis checklist and matched cyclone to virile, and you get one like 95% of the time. In the Arctic, so personally I think that the pressure gradient is the most important thing. So I really think that the interaction of the surface cyclone with the Beaufort High is really what's driving that pressure gradient. But I mean, I guess if you had like a strong anticyclone other than the Beaufort High then interacting with the cyclone, I guess.
Now it's also slow.
Yeah.
It put warm temperatures above freezing, but it's a slow process due to melt.
Yeah.
The important part is the Beaufort High either, so there is a high pressure that's semi-permanent there. It's the cyclones getting close to that high pressure and make it happen fast.
Yes.
Is there, in your research, have you noticed, are there any favored cyclone tracks that would lead to the greatest number of plurals? And also versus just the raw strength of the surface cyclone?
So believe it or not, surface cyclone strength is not statistically significant for those, again, taken from the reanalysis track lists and then comparing Arctic cyclones associated with viriles versus those not associated viriles. There's not a statistically significant difference in the strength. So I thought that was interesting, and
It's not how, basically it's not how strong the cyclone is, it's where the cyclone is.
it's where the cyclone is, and I think it's how it's interacting with the Beaufort High, and I think it's how thin the ice is underneath it. North Atlantic storm track, which is really active in the winter, you do see that cluster of viriles occurring there. So to answer your question, are there like cyclone track regions that are sort of like coupled or co-located with VRILs, that North Atlantic storm track is it's a really strong correlation.
Yeah, it's just basically getting to the point where if you have a favorite cyclone track that would lead, that you look back statistically and say, okay, this could be, this is a favorite track for a virile event versus if you have a cyclone entering from a different entering or exiting from a different region, so well, it's not favored.
Absolutely. Yeah.
Lastly, how much ocean action, as in the pressure gradient leading to surface ocean waves?
So what I have done so far, I haven't included analysis of the ocean. Based off of individual events observed by other people, the wind-driven ocean waves are an incredibly important dynamic of this process. Because those ocean waves are what can get deep into the marginal ice zone.
And also, it can not mention just move deep, but actually can help break up and
Right, absolutely. Those
get
are
those
really
chunks smaller.
mechanically important. So those ocean waves are likely incredibly important based off of observations of individual events, incredibly important. I don't have all of the data that I presented. It's just atmospheric data. So definitely something I want to dig into with using impasse coupled with CESM to get at different sea ice conditions in the modeling and have ocean feedback and all that jazz. Other questions?
Can you explain the Greenland issue? I didn't follow.
Okay. Greenland has really high elevation.
Sure.
And so surface pressure over Summit Station can be really, 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 really low.
Why not use MSLP?
Sorry, so why not use?
Yeah, instead of just surface.
No, I do use MSLP,
Right.
but converting it's by really low. I mean it's oh gosh, it can be in the 500s. And so bringing that down to sea level, there's always errors. And so in Arctic data, there's always low MSLP hotspots
Even.
on Greenland. Yeah. Needs Sarah. Sarah Borg's responsible for Greenland. She left.